Okay, so this is take 2 of the limiting reactants video. The previous one that I recorded didn't have any sound on it, so I'm going to record it again and put it up for y'all so you can look at it at home or for the online students or whoever needs it. Alright, so like we talked about in class, the basis of limiting reactants is that when you perform any reaction, you're pretty much never going to have the exact right amounts of each reactant so that they both get completely used up. One of them will always run out faster than the other one. All right, the basic idea there is think of it like when you're making hot dogs, right? You buy the buns in packs of 12 and the hot dogs come in packs of 8. So you're going to run out of hot dogs before you run out of buns. All right, that one that runs out first is what's called your limiting reactant. All right, the other one, the one that has some leftovers, that's called the excess reactant. All right, so those are the two terms you're going to need to keep in mind. Okay, another analogy we can look at here is say we're trying to follow a recipe, all right? And say we're making sandwiches, okay? If we look in our pantry and we have 6 pieces of bread, 12 pieces of lunch meat, and 5 pieces of cheese, and each sandwich calls for 2 pieces of bread, 3 pieces of meat, and 1 piece of cheese, well, based off of what we have, we can make 3 sandwiches, right? Our 6 pieces of bread are going to run out after that, and then we're going to have excess lunch meat and excess cheese. So no matter how much more meat or cheese we have, we can't make any more sandwiches, right? After 3, our reaction is done because we ran out of our limiting reactant, which was the bread. Okay, so as soon as your limiting reactant runs out, your reaction is finished and it can't make any more. All right, and so what that's going to look like in chemistry is something like this. So in this example, this one tells you how many moles of each of the 2 reactants you have. And it wants to know how many moles of oxygen will be produced from that. All right, so we've got 4 KO2 plus 2 H2O yields 4 KOH and 3 O2. So that's our equation. All right, and the problem tells us that we have 0.2 moles of our KO2 and 0.15 moles of our H2O. Those are the reactants that we're working with. All right, and so our first step needs to be to figure out which one of these is the limiting reactant. Which one of them is going to run out first. Okay, and to do that, we're going to use the same mole ratio step that we were doing yesterday or last week with stoichiometry. So we're going to pick one of these. It doesn't matter which one. You can pick either one and still figure it out. And use that to figure out how much of the other one we would need to react completely with this quantity of one of our reactants. So for this example, let's just say we pick the KO2 here. All right. So we're going to start with that, and we can ignore this 0.15 for now. So our coefficients for our mole ratio are going to be the 4 in front of the KO2 and the 2 in front of the H2O. So the left side of our proportion, we can say is 4 over 2. And we're going to say that is equal to this 0.20 over x. Okay. We're going to cross multiply here, do the butterfly method or whatever your teachers from math called it. So 4 times x is 4x, and 2 times 0.20 is 0.40. And then to get x by itself over here, we have to divide both sides by 4. So we come out with x is equal to 0.10. All right, so doing all that, what it tells us is how much of our other reactant we would need to completely react with 0.2 moles of the KO2. So that told us we need 0.10 moles of H2O. So if we need 0.10, and the problem tells us that we have 0.15, that means we have more than we need, right? So if you get where you find that, where you have more than you actually need, that means that is your excess reactant, all right? Which in turn means that the other one is your limiting reactant. Okay, and we could have done this the other way as well if we had started with our H2O instead. So if we wanted to set this up going the other direction, we could say our ratio would be 2/4. And we would put in this 0.15 over x. Do the same cross multiplication step. So 2 times x is equal to 4 times 0.15. So that's 0.6. Divide both sides by 2 to get x by itself. You come out with x equal to 0.30. So doing it that way tells us that in order for 0.15 moles of H2O to be reacted with completely, we would need 0.3 moles of KO2. In this case, we need 0.3. The problem says we only have 0.2, so we have less than what we would need, which makes it our limiting reactant. So you end up with the same answer either way you do it. It just depends on which one you start with, really. All right, so once we've done that to determine our limiting reactant, the next step is actually answering the question. And what it wants to know is how many moles of oxygen can be produced. So to find out how many moles of the product can be made, you're only caring about your limiting reactant. Because once that one runs out, the excess, whatever's left over of it, doesn't matter, right? Just like the lunch meat from the sandwiches that we talked about. Cut it out. Hey. Sorry, y'all. Okay, so you're going to use your value for your limiting reactant to set up and solve for how many moles of O2 you have. And this process here is just like it was with the stoichiometry as well. We're going from moles of our given molecule to moles of our target molecule. So we're going to use a mole ratio again to do that. Fisher, chill. So your coefficients in this mole ratio are going to be 4 from the KO2 and 3 from the O2. So it's going to be 4/3. And then this time it's going to be the 0.2 over x. All right, we do the same cross multiplication. So 4 times x is equal to 3 times 0.2, which is 0.6. And then you divide both sides by 4 so that they cancel out over here, and you get x is equal to 0.15. All right, so your answer to this problem would be that you can produce 0.15 moles of oxygen from the reactants that you were given. So your answer would just be 0.15 moles of O2. All right, so that's the process we're trying to follow. This next example is a little bit different. All right, and this one, instead of giving it to you in moles, it gives it to you in grams, and that's what most of the ones on your homework are going to end up looking like, where it gives you the reactant quantities in grams, and it asks for grams of the product. So this has that extra step of converting from grams to moles first, and then using that to do all of your mole ratios. So we've got HGO plus 2 Cl2 yields HgCl2 and Cl2O. All right, and the problem tells us that we have 135 grams of HGO and 68 grams of Cl2 as our starting quantities for our reactants. Okay, so anytime you're given mass in problems like these, your first step is going to be converting everything into moles. So just like we talked about when we reviewed it last week, or when we were doing stoichiometry problems, in order to convert from mass to moles, you have to divide by the molar mass. So we need to find the molar mass of our HGO. And if you look on the periodic table and find it, you'll see that the molar mass of Hg is 201, and the molar mass of oxygen is 16. And then in this molecule here, we just have one of each. So when you add them together, they come out as 217 grams per mole. All right, we also need to know the molar mass of our Cl2 for this molecule here. So if you look on the periodic table, chlorine's mass is 35. Multiply that by 2 because we have 2 chlorines in our formula here. And you get a total of 70 grams per mole. All right, you're going to take these molar masses and use them to convert each of these masses into moles by dividing. So we're going to say 135 divided by 217. And if you plug that into your calculator, can y'all see that? There we go. 135 divided by 217 comes out as 0.62 moles. And then we have 68 divided by 70 comes out as 0.97 moles. All right. So now we're at the point where we started our last problem, where we know how many moles of each of our reactants we have, and we need to figure out which one of them is going to be our limiting reactant. So to do that, we set up our mole ratio. And like I said last time, you can start with either one of these you want, and you'll still be able to figure out the answer. So we'll just start with the first one, the HGO, and our ratio of our coefficients there is going to be 1 over 2, right? There's no coefficient in front of here, so that just means it's a 1. So we can say 1 over 2 is equal to our 0.62 over x. 1 times x is x. 2 times 0.62 is 1.24. So that's all we got to do there. X is equal to 1.24. And then we compare. If we need 1.24 moles of this compound, and the problem says we only have 0.97 moles, that means we have less of it than we need, right? This value of what we have is smaller than what our mass says we should need. So if we have less than we need, that makes this our limiting reagent, and it makes the other one the excess reagent or reactant. Those words are kind of interchangeable, reactant and reagent. Okay. So now that we know which one is our limiting reactant, we can use that to figure out how much, sorry, that's a typo in there. The slide says oxygen. It should say Cl2O is what it's asking about. So let me fix that for y'all real quick. All right. So it wants to know how much Cl2O can be produced. So at this point, we're just doing this like any other stoichiometry problem once you figure out which one is the limiting reagent. You're going to use this value of the limiting reactant that we have, and we're going to convert that to the number of moles of Cl2O that can be produced based off of the mole ratio. So our mole ratio between these two compounds is 2 to 1, because this one has a coefficient of 2 and this one doesn't have a coefficient. So we can say 2 over 1 is equal to 0.97 over x. We do our cross multiplication, so we get 2 times x is 2x. 0.97 times 1 is 0.97. And then to solve for x, we have to divide both sides by 2. So we come out with x is equal to 0.49. All right, that tells us how many moles of the Cl2O are pronounced. And then your last step, just like the stoichiometry problems we were doing last week, is to convert from moles to mass. All right, so cut it out. He's chewing on my feet. All right, so your last step, we're converting this from moles to mass. So we're going to figure out what the molar mass of this compound is, and then multiply it by the number of moles that we have. So we've got Cl and O. Same as before, chlorines weigh 35 each, and oxygens weigh 16 each. And then we have 2 chlorines and 1 oxygen. So that's 70 and 16, and you add them together for a total of 86 grams per mole. That's your molar mass. And then we're going to multiply that by our 0.49 moles in order to find the mass of the product that's created. So 86 times 0.49 comes out as 42.14 grams. And that would be your final answer here. Okay, so just like the stoichiometry problems last week, these are long problems with lots of steps, lots of spaces where you can make a simple mistake and throw yourself off. So take your time when you're going through them. And I would recommend that you make sure you've done the stoichiometry homework and watched that video and read those notes before you attempt these ones, because a lot of the skills are the same, and the more practice you have on them, the better it's going to be before you start these more complicated ones. All right, let me know if you have any questions.